Hello there, and welcome. I'm so glad you found your way here. Maybe your eyes are already heavy. Maybe your mind just needs something beautiful to rest on, a thought too big to finish and too soft to resist. Either way, you're in the right place. You don't need to do anything now but listen. Let your breath deepen. Let your muscles go quiet. Let your thoughts blur like distant light. Because tonight, we're leaving Earth behind. We're going to drift into the life and death of stars. Not just facts, but revelations. You'll hear things that sound impossible, but are true. Things born in nuclear fire, and things ending in collapse and silence. Stars are not just points of light. They are engines of time, cradles of matter, and the ultimate storytellers of the universe. We'll float from first sparks to final fades. From stellar nurseries to black holes, from slow-burning giants to explosions so bright they outshine galaxies. Some stories are calm, some are violent, all are true. Now take a deep breath, let your day drift away, and let's travel together into the quiet corners of the universe. Far from city lights, deeper than the darkness of any night you've ever known, there are clouds that never glow. They drift quietly through space, silent and invisible, made of gas and dust so sparse that they would seem like nothing at all if you stood within them. And yet, these are the places where stars are born, not with explosions or brilliance, not with noise or light, but with stillness, with waiting. These are the cold cradles of creation, the stellar nurseries, and some of them have been waiting for longer than life has existed on Earth. Inside these clouds, hydrogen atoms move slowly, too slowly to collide with much energy. Temperatures hover just above absolute zero, mere degrees away from the coldest temperature possible in nature. At this point, everything is subdued. Motion barely exists. The particles within don't rush, don't scatter. They huddle, waiting for a nudge that might never come. You might imagine a storm of gas, a swirling maelstrom, but this is more like fog in a forgotten valley, quiet, low, suspended, and yet, even here, gravity works. It pulls ever so gently on every speck of matter. Over time, thousands of years, millions, sometimes more, the gas begins to clump. Small pockets of slightly denser material gather a little more gas than their neighbors. These pockets grow heavier. Gravity strengthens. The process builds upon itself, like whispers becoming weight, like thoughts thickening into dreams. The cloud resists. Thermal pressure, magnetic fields, turbulence. Each one tries to hold it back, but gravity is patient. It does not hurry. It has all the time in the universe. In some regions, collapse never begins. The gas is too thin, the temperature too warm, the balance too stable. These clouds drift endlessly, never forming stars. They are possibilities unfulfilled, dark potential that floats quietly through the galaxy. Their silence is not failure. It is a kind of suspended promise, the cosmic equivalent of a pause that never ends. But in others, something changes. Perhaps a nearby star explodes in a supernova, sending a shockwave through the cloud. Perhaps two clouds collide. Perhaps nothing more than the subtle accumulation of mass reaches a tipping point. Whatever the cause, a collapse begins, and once it starts, it accelerates. The core of the clump compresses, drawing in more material. It heats, slowly at first, then faster, as atoms crowd closer and closer. This is not yet a star. There is no light, no fusion, but something is stirring. This growing core is called a protostar, a seed of fire still wrapped in shadow. Around it, a disk of gas and dust forms, spinning gently like the arms of a spiral. Material flows inward along this disk, feeding the protostar like a river of potential. Inside, pressure mounts. Atoms are pressed together with increasing force. Hydrogen atoms, the most basic in the universe, begin to brush against each other so closely that their boundaries blur. The temperature climbs past 1,000,000 degrees, and then, suddenly, something changes. Fusion ignites. Hydrogen atoms fuse into helium, releasing light, heat, and energy in a surge that pushes back against the crushing force of gravity. A balance is struck. Gravity pulling inward, fusion pushing outward. This moment is the birth of a star. Not with fanfare, not with sudden brightness, but with a quiet, brilliant equilibrium that can last billions of years. A steady flame where there was once only cold. The light, at first, may not escape. The protostar is still surrounded by a cocoon of dust and gas, veiling it from view. But it shines, nonetheless. Over time, the stellar winds will clear the surrounding space, revealing a new sun suspended in the void. Perhaps it will have planets. Perhaps it will shine on nothing but emptiness, but it will shine. Some of these newborn stars form in groups. Stellar nurseries are rarely solitary places. A single collapsing cloud can give rise to dozens, even hundreds of stars. They light up together like fireflies in a field, illuminating the gas that gave them birth. These regions become nebulae, glowing clouds tinged in pinks and blues, shaped by winds and radiation. For a time, they are among the most beautiful places in the galaxy. But eventually, the nursery fades. The gas is used up or blown away. The stars drift apart. Others are born alone, in smaller clouds or at the edge of greater ones. They form quietly, far from their siblings. These solitary stars may live out their entire lives in isolation, their light never touching another world. But even they owe their existence to the dark. And sometimes, a star is almost born, but not quite. When the collapsing clump isn't quite massive enough, when the temperature never gets high enough for fusion, a different kind of object forms. These are brown dwarfs. Failed stars that glow faintly with heat, but never ignite. They hover between planets and stars, not quite one, not quite the other. And they, too, drift through the galaxy in silence. Even the stars that succeed do so because of failure, because gravity overcomes resistance, because gas condenses instead of dispersing, because cold gives way to fire. Their birth is not guaranteed. It is the result of balances tipped, of chances taken, of forces that yield to other forces in just the right way. So when you look up at the night sky and see a star twinkling, remember that it began in the dark. It began in a place where light could not reach, where nothing moved quickly, where silence stretched for millions of years. It waited, it gathered, it fell inward, and one day it began to burn. The next time you close your eyes, imagine yourself drifting in one of those clouds, weightless, unlit, suspended. Imagine waiting not days or weeks, but eons. And then, feel the warmth begin at your core. Not sudden, not violent. Just a pressure, a brightness, a beginning, a star born from the dark. In the beginning, there is no flash, no sparkle, no burst of brilliance. The start of a star's life is hushed, buried deep within clouds so thick that not even light can escape. Here, in the folds of interstellar dust, warmth grows where once there was only cold. It happens quietly, like a slow exhale in the dark. Gas collapses inward, pulled by gravity's gentle insistence. And at the heart of this collapse, a core begins to form. It does not shine, not yet, but it begins to stir. The growing core is what astronomers call a protostar. It isn't a true star, not in the way we think of them. It does not emit its own light. Instead, it glows faintly in the infrared, its heat cocooned within layers of dust and gas. Around it, the collapsing cloud doesn't vanish, but reshapes itself into a swirling disk, feeding the protostar with a steady flow of matter. The rotation of the disk brings a strange kind of order to the chaos. Material spirals inward, flattening and aligning, like threads being pulled into a whirlpool. Slowly, the core becomes denser. Pressure builds, temperature rises. Still, it does not shine. Inside the protostar, atoms are packed closer together than they have ever been. Hydrogen atoms collide, rebound, collide again. But there is not yet enough heat, not enough pressure to fuse them. For now, the growing heat comes from friction and compression, not from the alchemy of nuclear reactions. The protostar is a pressure cooker in space, building its energy over tens of thousands, sometimes millions of years. During this time, it pulses. It breathes in a rhythm of expansion and contraction, finding temporary balance and then losing it again. These are not stable years. They are the growing pains of a star not yet born. Some protostars go through outbursts, brief flares of energy, when a sudden surge of gas crashes into the core. These flares light up the surrounding dust like a paper lantern in fog. Then the light fades, swallowed again by the shroud. If you could drift nearby, through the dim glow of the dusty cocoon, you wouldn't see much. You might feel a slight warmth, like the air near a smoldering ember. You might see eddies of dust lit by faint reflection. But the star is still hidden, still waiting. Eventually, if the protostar gathers enough mass, a threshold is crossed. Deep within its heart, the pressure and temperature climb to extraordinary levels, millions of degrees. Hydrogen atoms begin to fuse into helium. It doesn't happen all at once. It's not a switch flipping, but a slow ignition. The fusion begins gently, a whisper of power that grows into a steady fire. This is the moment the star is born. Not when it first becomes visible, not when its light breaks through the dust, but when fusion begins. At that instant, the star becomes self-sustaining. It no longer depends on the collapsing gas around it. It generates its own energy. Gravity still tries to pull it inward, but now the fusion at its core pushes back with equal force. The two forces balance. This balance is fragile but resilient. It will last as long as the fuel does, which for many stars means billions of years. From the outside, the difference may not be dramatic, but inside, everything has changed. The star now emits a steady stream of light, though that light may still be wrapped in veils of dust. Over time, stellar winds begin to clear away the cocoon. The newborn star starts to shine in visible light, finally revealing itself. It carves a hollow in the cloud from which it was born, a glowing bubble that expands slowly, gently pushing the remnants of its birth outward, if there are others nearby. Siblings formed in the same cloud. They may do the same, their light overlapping in a quiet chorus of radiance. Some stars never reach this point. They collapse partway, then stall, never achieving the conditions for fusion. These become brown dwarfs, failed stars, glowing weakly with leftover heat, but never igniting. Others form so quickly and with such mass that their fusion begins while they're still deeply embedded in their dusty cocoons. These massive stars live fast, burn hot, and die young. But no matter the size or future, every true star begins with this same ignition, a hidden flame catching hold in the darkness. It's strange to think that all the light we see at night, every star overhead, every twinkle, once came from this quiet beginning. No star starts bright. All of them, even the giants, begin in collapse, in darkness, in silence. And even the sun, our sun, followed this path. It spent its earliest years wrapped in shadow, its warmth locked within, its light still just a promise. There was a time, billions of years ago, when it too was only a protostar, gathering strength, waiting to shine. That first moment of fusion wasn't something anyone could see. There were no eyes to witness it. But from that moment forward, the sun began to push against gravity, to shine, to warm the small pieces of rock and ice around it. Eventually, one of those pieces became Earth. And eventually, that light reached here, to your skin, to your breath, to this moment. and it all began with collapse. The journey from gas cloud to star is not a leap. It is a slow gravitational falling inward, a surrender to pressure and heat. But from that surrender comes creation. From darkness, light. From silence, energy. Each star is a quiet victory of physics over chaos, a moment when the universe, without trying, makes something stable, something radiant. And somewhere, right now, in the quiet corners of distant galaxies, it's happening again. A protostar is forming, dust is swirling, heat is building, and fusion, soon, will begin. The universe does not measure stars by their beauty or their brightness. It measures them by mass. From the moment a star begins to form, its mass is its destiny. Not just how large it will become, but how hot it will burn, how long it will live, and what kind of death awaits it. In the quiet of the protostar's birth, the scale has already tipped. The future has already been chosen. A star with low mass will never burn hot enough to dazzle the cosmos. It will glow softly, often in red, and remain small, steady, and faint. These stars, known as red dwarfs, are among the most common in the universe, though most go unnoticed by the naked eye. They sip their hydrogen slowly, taking their time. Some may live for tens of billions of years, others for trillions. They are the slow burners, the quiet companions, the cosmic elders in training. Not one has died yet. Not in all of cosmic history, because the universe itself is not old enough to have seen one reach the end. Their light is gentle, almost reserved, like embers in a deep fire that never quite goes out. Then there are stars like our sun, middling, moderate, balanced, born with just enough mass to glow bright in the sky, warm enough to cradle life, but not so massive that it races toward oblivion. The sun's fate is a long, patient unfolding. It will burn for about 10 billion years, and halfway through that life, it hosts us. Its mass has determined that it will one day expand into a red giant, shed its outer layers, and leave behind a white dwarf, a dense, hot ember that will cool for eons. This is the gentle ending of a medium star. It is not peaceful exactly, but it is not violent either. It is transformation, not destruction. But if a star is born with more mass, 5, 10, 20 times the mass of the sun, everything changes. These stars burn fast. Their cores are furnaces of unstoppable pressure, where hydrogen is consumed at an incredible pace. Their surfaces are blinding, blue-white with intensity. Their winds strip away their outer layers. They pulse with energy, and they die young. Some live for only a few million years. A blink in cosmic time. From the moment fusion begins, the clock is already running fast. These are stars that live like firecrackers, brilliant, intense, and short-lived. Their deaths are not gentle. When the fuel runs out, when the core can no longer hold the weight pressing down upon it, collapse happens suddenly. In a fraction of a second, gravity wins. The star implodes and then rebounds in an explosion of unimaginable energy. This is a supernova, a flash so bright it can outshine an entire galaxy. It is the final act of a star that had too much to hold on to. And what is left behind is never the same. Some leave neutron stars, city-sized spheres of matter so dense that atoms themselves are crushed. Others, more massive still, leave nothing at all but a black hole, a region of space where gravity is so strong that not even light can escape. These stellar remnants are echoes of the mass they once carried, fossils of stars that lived too hot and burned too fast. Mass also shapes a star's color. Small, cool stars glow red or orange. They are like coals, glowing from within, not seeking attention. Medium stars like the sun shine in white, a balanced blend of warmth and power. The hottest, most massive stars blaze in blue, their surfaces reaching tens of thousands of degrees. These colors are not just aesthetic. They are signatures of temperature, of energy, of lifespan. They are messages written in light about a star's nature and future. Even the way a star moves through its life, how it expands, contracts, pulses, or stabilizes, is guided by mass. Some stars swell into giants, others become supergiants. Some remain compact, their surfaces calm. Some shed layers in great waves of solar wind. Others lose their envelopes in fits and surges. And all of this, every flare, every pulse, every quiet breath, is a consequence of how heavy that star was when it began. But mass does not come alone. It often travels with companions. Many stars are born in pairs or systems of 3 or more. In these relationships, mass can be shared. A smaller star might siphon material from a larger one, changing both of their fates. A white dwarf might grow too heavy and explode. A binary system might merge into something new. Even after birth, even after light, a star's mass can shift, rewriting its future in real time. But even these shifts are guided by the initial conditions. The blueprint of mass always underlies the evolution. From a distance, stars seem like they should all be the same, points of light in the dark. But their differences are profound. 2 stars can be born minutes apart in the same cloud and live entirely different lives. One might still be shining long after galaxies have collided. The other might already be gone, reduced to dust or crushed into silence. The difference lies in weight, in mass, in the invisible scale that sets their fate from the beginning. And yet, stars don't know their fate. They don't resist it or rush toward it. They simply live according to the rules of pressure and fusion, time and fuel. A massive star doesn't burn out in tragedy. It burns as it must. A dwarf doesn't last forever because it tries. It simply sips what it has. There is no will in the flame, only physics. And still, there is something beautiful in that inevitability. It means that every star you see, whether it glows faintly red or blinding blue, is telling you something about its path, about how long it has, and what will become of it. The sky is not just filled with stars, it is filled with stories written by mass, lifetimes in light, fates measured in fusion. Some stars are already gone, their light still on its way. Some have barely begun. Some will never end, not in any time that matters to us. But all of them are shaped by the same force. All of them are balanced between gravity and energy, burning in quiet conversation with their own weight. And all of them, from the smallest ember to the largest inferno, carry a future they cannot escape. From their first breath, it is already written. If you've ever looked up on a clear night and seen stars twinkling softly, you've probably noticed how they seem to shimmer in color. Some pale blue, others yellowish, a few almost red. But that sparkle, that color, that flicker, it lies to us. Or maybe not lies, exactly, but bends the truth through layers of atmosphere and perception. The true colors of stars are more precise than we think, written not in poetry, but in physics. A star's color is not just a trick of light, it is its temperature. The hottest stars blaze in blue. Their surfaces can reach temperatures of 30, 40, even 50,000 degrees Kelvin. These stars are rare, massive, and short-lived, their light sharp and brilliant, their energy pouring out across the spectrum. But their blue isn't like the soft blue of a calm sky. It's fierce, electric, the kind of blue that borders on white, that hums with invisible heat. And then, stranger still, some stars glow in ultraviolet, emitting more energy than human eyes can see. To us, they would appear ghostly, colorless, or oddly dim, but in reality, they are blazing beacons, their brilliance lost to our biology. Cooler stars shift toward red. These stars burn at just a few thousand degrees, and their light is more gentle. It radiates longer wavelengths, the kind of light that feels like warmth even when it's faint. If you could see a red dwarf star up close, without going blind or vaporizing, you'd see a dull, steady glow, not flickering, not sharp, but constant. These are the stars that last the longest. They do not need to burn brightly to endure. Their red hue is a signature of restraint, of slow burning over trillions of years. In the middle sits our sun. To our eyes, it looks yellow, sometimes golden, sometimes almost orange, depending on the time of day. But that's an illusion. In space, beyond Earth's atmosphere, the sun is white, perfectly balanced white. It emits a nearly even mix of all visible wavelengths, a spectrum that combines into a pure, neutral light. The yellows and oranges we see from the ground are artifacts of scattering, of air molecules bending light and filtering the blue away. It's the same reason the sky is blue and sunsets are red. We see the sun not as it is, but as Earth allows it to appear. And even beyond the atmosphere, human vision can only grasp part of the truth. The visible spectrum is just a thin sliver of the electromagnetic range. Many stars pour out energy in colors we can't perceive, in ultraviolet, in infrared. To telescopes tuned to these frequencies, the sky looks entirely different. Cold stars radiate in infrared, glowing like embers on a frozen landscape. Hot stars shine with radiation too energetic for eyes to register. Some stars beam with intense violet light, but because our eyes are less sensitive to violet than to blue or green, and because the atmosphere absorbs so much of that light, we almost never see them for what they are. Their brilliance is hidden in plain sight. The color of a star, then, is not just appearance. It is a measurement. It tells us how fast the atoms on its surface are vibrating, how much energy they're giving off, how its photons behave as they scatter through the vacuum of space. A star's color is its temperature worn like a cloak, woven from light. And like temperature, it is precise. Astronomers can look at the color of a star and know within a fraction of a percent how hot its surface is. They don't need to touch it, or even get close. Light alone is enough. This relationship between color and temperature is one of the few constants in a universe full of mystery. It means we can look across millions of light years and know the temperament of a star just from its hue. We can guess its mass, its age, even its future. Blue stars burn hot and short. Red stars burn cool and long. White stars like the sun live balanced, middle-aged lives. Color becomes biography. And sometimes, the atmosphere plays tricks. Stars near the horizon seem to flicker more, their colors dancing rapidly. This isn't because the stars themselves are unstable. It's the result of looking through more air, more turbulence, more scattering, more distortion. The twinkle of a star is not in the star. It's in the air between you and it. The higher the star is in the sky, the less it flickers, the truer its color becomes. But even then, our perception lags behind the truth. We are not built to see stars as they are. We're built to see them as they appear to us from here. Still, the colors do reach us, and they tell quiet stories. A star that seems reddish might be nearing the end of its life, expanding into a giant, shedding its outer layers. A star that's bluer than its neighbors might be younger, hotter, heavier, living fast, and destined to end in violence. In a dark sky, away from artificial lights, you can sometimes pick out these variations by eye. Vega shines with a bluish tinge. Betelgeuse glows orange-red. Sirius flashes white-blue like a frozen flame. The sky becomes a gradient of heat, a map of thermodynamics painted in points of light. There is elegance in this simplicity. Color as temperature, temperature as identity, light as a messenger of heat. It's one of the few things in astronomy that feels almost intuitive, like something we should have always known. And yet, even now, there are colors we'll never truly see. Stars glowing in violet and ultraviolet, their beauty invisible to us except through instruments. We know they're there. We can detect their presence. But the experience of their color is forever out of reach. And maybe that's part of the wonder, that something as fundamental as color can still contain secrets, that stars, even in their simplicity, hold back just enough to remain mysterious. They shine across time and space, each one wrapped in a temperature you can see, if you know how to look. Each color is a story, a measurement, a whisper of heat across a vacuum too vast to imagine. And still, somehow, it finds its way here, to your eyes, to the sky above you, to the quiet part of night where everything glows just a little. Most stars rush through life like they're being chased. They flare and blaze, exhausting their fuel in dazzling shows of brilliance. But not all. Some stars are born into a different rhythm, one so slow it almost seems like stillness. These are the red dwarfs. Small, dim, and unassuming, but quietly extraordinary. They are the patient ones, the survivors, and in the end, they may be all that remain. A red dwarf forms the same way any star does. Through collapse, through the slow gathering of gas and dust, until the pressure becomes enough to ignite fusion. But they form with the bare minimum mass needed to sustain that fire, just enough to fuse hydrogen into helium, and nothing more. This scarcity gives them their gift. Because they burn so little, so softly, they last so long. Their fusion is slow and balanced, a steady simmer rather than a roar. Where larger stars blaze through their fuel in a few million or billion years, red dwarfs can last hundreds of billions, even trillions, lifetimes beyond imagining, longer than the current age of the universe itself. No red dwarf has ever died. Not once, not anywhere. The universe is still too young. These stars have been glowing gently since nearly the beginning, and they will still be glowing long after everything else is gone. After the giant stars have exploded, after the suns like ours have swelled and faded, after galaxies have aged and merged and dimmed, red dwarfs will remain, scattered embers in the dark, still burning, still shining, long after everything we know has passed. They are not dramatic. They do not go supernova. They don't collapse into black holes or scatter elements across the cosmos. They live and burn and fade so quietly that they seem almost forgotten. But in that quiet, there is something profound. A red dwarf uses nearly all of its fuel. Where larger stars burn through their cores and leave vast envelopes untouched, a red dwarf mixes its interior, slowly cycling its hydrogen so that nothing is wasted. This efficiency is part of its magic. It lives not just long, but well. A balanced life, without waste, without fury. If you were to visit a red dwarf, you might not even see it at first. Many are so faint that from just a few light years away, they're hard to detect. Their light doesn't pierce the dark the way hot stars do. It glows like a coal buried under ash. Dim, deep, red, steady. Their surfaces are cool by stellar standards, just a few thousand degrees, and they don't emit much in the visible spectrum. But they're warm enough to host planets, and some of those planets may even be close enough for warmth without being scorched. In fact, some scientists believe that red dwarfs might be the best homes for life in the long run, not because they're ideal, but because they endure. If life begins around one, it has trillions of years to grow, adapt, evolve. Civilizations could rise and fall 100 times over, and the star would remain unchanged. There is time in abundance, time enough for everything, but red dwarfs aren't without complications. Their youth can be stormy. Some flare wildly, sending out bursts of radiation that could sterilize a nearby planet or strip its atmosphere. Others remain calm, their energy consistent and predictable. The temperament of each star is different, shaped by rotation, magnetism, and time. And even if they start volatile, most red dwarfs settle as they age, their flares softening, their pulses slowing. They mature into peace. Eventually, even these stars will dim. Not quickly, not in a way that's easy to witness, but gradually, over trillions of years, their hydrogen will run low, their fusion will falter. They won't die explosively. There will be no last flare, no final breath of light. They will simply cool, shrink, and fade into black dwarfs, cold, dense remnants that no longer shine. But that moment is so far in the future it defies comprehension. The universe itself may be unrecognizable by then. Galaxies stretched thin, stars scattered, the fabric of space pulled into stillness, and somewhere in that distant twilight, a red dwarf will give off its final whisper of warmth. These stars teach us something about endurance, that brilliance isn't the only kind of power, that lasting can be just as miraculous as shining. They live so long not because they are strong, but because they are careful, measured, modest in their needs, and generous in their time. They are a kind of cosmic patience. Even now, if you look up, many of the stars you see are not red dwarfs. You're more likely to see the bright ones, the massive, short-lived giants. But they are fewer in number. Red dwarfs vastly outnumber them. They form more often, and they stay longer. The night sky is shaped by what we can see, not by what exists. Most stars are hidden from us, too dim, too distant, too quiet. But they're there, woven through the fabric of every galaxy, lighting the dark with slow-burning persistence. And when the last brilliant star has faded, when the great beacons have gone out, the red dwarfs will still be there, burning slowly, watching the dark grow. They will be the final lights of the cosmos, the last warmth, the final stars. In that distant future, long after the age of starlight, someone, or something, might look into the night and see a single point of red, faint, unwavering, ancient. And that light will not be the last gasp of a dying fire. It will be the heartbeat of a star that never rushed, never demanded attention, never needed more than what it had. A star that lived not for glory, but for time. A red dwarf, still burning, still holding on. Supergiant stars are not quiet things. They burn with a furious brilliance, a light so intense it can be seen across galaxies. From a distance, they look whole, seamless spheres of fire, glowing white or blue, sometimes red depending on their age and size. But inside, beneath the surface of all that radiance, they are something stranger, not solid, not uniform. A supergiant star is a layered furnace, a slow implosion wrapped in light. As these stars age, their cores change. They burn through hydrogen first, fusing it into helium over millions of years. Then, when the hydrogen is gone, the core contracts, heats, and begins fusing helium into heavier elements like carbon and oxygen. With each new stage, the process repeats. Burn, collapse, ignite, burn again. And each time the core grows heavier, the layers above it build like rings of flame around a dying center. Like an onion, but made of plasma and pressure, each shell burning a different element, stacked with increasing intensity. Helium fuses near the core. Above it, a layer fusing carbon. Above that, neon. Then oxygen, then silicon. Each layer smaller, each one burning faster than the last. The deeper you go, the stranger it becomes. These aren't stable furnaces. They're races against time. The outer layers may take hundreds of thousands of years to consume their fuel. But as fusion pushes toward heavier elements, the clock begins to speed up. Carbon burning might last only 1,000 years. Neon, just a year or so. Oxygen fuses in months. Silicon, only days. Then hours. Then minutes. Each stage faster than the last, like dominoes falling inward, towards something that can't be stopped. Because at the very center, something is forming that changes everything. Iron. It does not fuse. Unlike lighter elements, iron cannot release energy through fusion. Trying to fuse it costs energy instead of giving it. It is the dead end of nuclear reactions, the point at which the star's engine stalls. But the core keeps filling with it anyway, atom by atom, under pressures too vast to comprehend. It builds silently, invisibly, accumulating until the balance breaks. And when it does, it breaks completely. The moment comes without drama from the outside. The star still glows. Its surface is quiet. But inside, the iron core grows too heavy to support itself. Gravity, always patient, finally wins. In an instant, the core collapses. It falls in on itself at a quarter the speed of light. Atoms crushed, protons and electrons forced together into neutrons. The outer layers, still burning, haven't even registered what's happened below. The collapse moves faster than light can carry the news. And then everything changes. The inner core stops, suddenly too dense to shrink further. The matter rebounds, slamming into the falling layers behind it. That shock wave surges outward. Combined with a burst of ghostly neutrinos released in the chaos, the shock finally overcomes the weight of the star, tearing its outer layers apart. The surface, once calm, erupts. The light from that explosion can outshine an entire galaxy for days. This is a supernova, the brief, blinding death of a star that spent millions of years slowly building toward it. But before that moment, before the flash, before the blast, there is a strange kind of hush, a period where everything inside is rushing toward collapse, but nothing yet shows it on the outside. The layers still burn, the star still shines, but time has begun to compress. What took millions of years now happens in hours. Shells of fusion snap into existence, then vanish. Oxygen flares and is gone. Silicon builds sulfur, then iron. The core becomes a neutron-rich ghost, its temperature soaring into billions of degrees, its pressure unthinkable. But there is no way to relieve that pressure, no way to burn what comes next. It's a slow build to a sudden end, and it's not chaotic, it's precise. Every shell forms where the physics demands it. Each reaction unfolds with perfect timing. The process is violent, but it is also ordered, as though the star has been planning this all along. It's the last thing it knows how to do. From the outside, you would never guess. A supergiant nearing collapse still looks like a star. It hasn't changed color. It hasn't dimmed. Its light has traveled for hundreds or thousands of years to reach us, and even if we're watching in real time, we only see the calm surface. We don't see the burning shells nested deep within. We don't see the iron core, silent and deadly, growing by the second. We don't see how fast time is running inside. And then, one day, that light simply ends. Or, for a moment, it becomes something else. An explosion, a brilliant flare of energy and debris, a release of everything the star had ever been. In the aftermath, what's left depends on the mass. If the core is small enough, it becomes a neutron star, dense, fast spinning, strange. If it's large enough, not even that remains. The collapse continues past the point of structure, past the point of resistance, until the core becomes a black hole and nothing escapes. All of this begins with layers, with shells of fire, nested like secrets, wrapped around a center that cannot hold. The structure is elegant, fragile, beautiful, in the way only something doomed can be. A supergiant's final days are not just about collapse. They are about sequence, about how quickly complexity can fall apart. A star that took millions of years to build its identity comes undone in the span of a human breath. And yet, the explosion that follows is not the end of its story. It is the beginning of many others. The elements forged in those final moments, gold, uranium, the calcium in your bones, the iron in your blood, are thrown into space, scattered across the galaxy. They will become part of new stars, new planets, new lives. They are the ashes of something enormous, burning still in another form. But before all that, there is the star itself, giant, hollow, layered like an onion, filled with fire and fusion and inevitability, waiting, burning, folding into itself faster and faster until time runs out. When a low-mass star dies, it doesn't explode. It doesn't shatter across the galaxy or collapse into darkness. It simply lets go. Gently, quietly. It sheds its outer layers in a final breath of light, casting off gas and dust into space like a slow, radiant sigh. What remains is something small, dense, and unyielding, a white dwarf, the stripped-down heart of a once-living star. It doesn't burn anymore. There is no fusion inside it, no fire feeding its glow. The star's energy source is gone, spent after billions of years of steady fusion. What's left is not a furnace, but a memory of one. A white dwarf shines only because it is still hot, still radiating the heat of what it used to be. Over time, that heat will bleed away into the emptiness of space, but that cooling takes billions, even trillions of years, far longer than the universe has existed. So for now, they still shine, dimly, steadily, like embers pressed deep into a pillow of ash. They are small, roughly the size of Earth, though their mass is close to that of the sun. That kind of compression defies intuition. Imagine a sun's worth of matter packed into a planet-sized shell. The density becomes staggering. A single cubic centimeter of a white dwarf, something no larger than a sugar cube, would weigh several tons. This is not just heavy, it's a weight that bends imagination. Electrons are crushed into strange configurations, held together by quantum pressure, a force that resists further collapse, not with heat or movement, but with the bizarre laws of physics that govern the very small. It's called electron degeneracy pressure, a boundary not of muscle or motion, but of quantum resistance, and it holds. Inside, there is no structure as we understand it, no crust, no mantle, no core. A white dwarf is a star that's been squeezed past familiarity. Its matter is degenerate, stripped of its usual order, packed until atoms no longer behave like atoms. There is no fusion because there is no space for it. The particles are too crowded, too compressed. All that remains is cooling, slow, inexorable, and deeply quiet. Over time, the white dwarf dims. It sheds its heat like a stone dropped into a cold sea, a little at a time. There are no pulses, no outbursts, just a steady decline. If the universe lasts long enough, white dwarfs will become black dwarfs, cold, invisible husks. But we've never seen one. The universe is too young. Every white dwarf ever formed is still out there, glowing faintly in the dark. They are stellar fossils, each one a relic of a star that lived and died long ago. The path to a white dwarf begins with a sun-like star growing old. When hydrogen in the core runs out, the core contracts and heats, and the outer layers expand. The star becomes a red giant, enormous and bloated, shedding material into space. Helium fuses for a while, forming carbon and oxygen. But the star is not massive enough to fuse anything heavier. Eventually, even helium runs out, and the outer layers peel away completely, forming a glowing planetary nebula, named not for planets, but for the round shapes early astronomers saw through telescopes. In the center of that nebula, exposed and brilliant, the white dwarf is born. What's strange is how long it takes to change after that. A white dwarf is almost perfectly stable. It won't collapse unless it gains too much mass from a nearby companion star. It won't expand or pulse. It simply is. The light it gives off is residual, a slow exhale of ancient heat, and the temperature, at first, is incredible. Fresh white dwarfs can be hotter than most stars, over 100,000 degrees, but because they're so small, they don't radiate that energy quickly. They remain hot for billions of years, cooling so slowly it's almost imperceptible. They can exist alone, drifting through space, or they can orbit other stars. Some live in binary systems, bound to still-living companions. Sometimes they accrete material from their neighbors, feeding off stolen gas. If a white dwarf collects enough mass this way, approaching a limit known as the Chandrasekhar limit, about 1.4 times the mass of the Sun. It can collapse further or explode as a type Ia supernova, a sudden return to violence from an object thought to be quiet. But most white dwarfs never reach that point. They don't feed, they don't grow, they just cool. They are hard to see with the naked eye. Their light is dim, especially compared to younger, larger stars. But they're not rare. In fact, the majority of stars in our galaxy, those in the low to medium mass range, will end as white dwarfs. That means that white dwarfs are the most common end state of stars. They are not unusual. They are the future. Our Sun will become one in time. In about 5 billion years, it will swell into a red giant, lose its outer layers, and leave behind a white dwarf core. That core will persist long after Earth is gone, long after the solar system has changed or drifted apart. The Sun's death will not be explosive, but it will be final. And what remains will continue on in silence, glowing faintly as the memory of a star. There is something solemn about white dwarfs. They are endings that last longer than the lives they conclude. They are quiet, enduring, almost forgotten. Objects that resist change by simply having nothing left to give. No fusion, no fuel. Just heat, mass, and the strange geometry of matter packed too tight to collapse. They don't demand attention, but they deserve awe. Not because they shine the brightest or burn the hottest, but because they last, because they mark the threshold between what a star was and what it can no longer be. A white dwarf is not a failure. It is the natural conclusion of a long life lived in balance. And when everything else has passed, it remains. A dense, glowing ember in the dark. Still warm, still here, still waiting. Most stars don't live alone, though we often imagine them as solitary suns blazing across an empty night. Many are born into partnerships, 2 stars orbiting a shared center, bound not by choice but by gravity's quiet insistence. Binary stars are not rare. They are the rule more often than the exception. And when stars are paired, their lives are no longer just about fusion and time. They become stories of interaction, of dependence, of influence, of fates that shift simply because another sun is near. In a binary system, both stars form together, born from the same collapsing cloud of gas. At first, they may seem to grow independently, each one pulling in its own material, building its own core, heating in its own way. But they orbit one another from the beginning, locked in a gravitational dance. How close they are, how massive each one is, how fast they orbit. These details shape everything that comes after, because in such a system, one star can profoundly change the other, sometimes in quiet ways, sometimes in ways that lead to spectacular endings. As stars evolve, they change shape and size. When a star begins to expand into a red giant, its outer layers puff outward, growing thousands of times larger than before. If its companion is close, that swollen outer envelope can cross a gravitational boundary called the Roche lobe. Beyond that invisible surface, the gas is no longer bound to the expanding star. It becomes available to its partner. The other star begins to draw it in, not forcefully, but inevitably. Gravity does the pulling. The red giant becomes a source, its companion, a thief, or maybe a rescuer. It depends on how you look at it. This process is called mass transfer, and it can go on for millions of years. A star that might have burned slowly and lived gently alone can be stripped of its mass by its companion. That loss changes everything. Its temperature, its pressure, the way it burns fuel, the path it will take toward death. A star that gains mass can be pushed into a different fate as well. A once small star might swell beyond its limits. The balance of life is disrupted. Time bends. The future shifts. In some cases, this exchange is stable. One star donates mass, the other accepts it, and they both adapt. But in others, the flow becomes chaotic. The material piles up faster than it can be absorbed. Accretion disks form, vast spirals of gas circling the receiving star, heating with friction, glowing in ultraviolet light. The system brightens, pulses, flickers with energy. And sometimes, if the star receiving matter is a white dwarf, something much more dramatic can happen. A white dwarf is already dense, already near the edge of stability. It can only hold so much mass before it collapses under its own gravity. The limit is precise, about 1.4 times the mass of our Sun. This is known as the Chandrasekhar limit, and it is a kind of cosmic tripwire. As the white dwarf siphons more and more material from its companion, it inches toward this boundary. Slowly, silently, it fills with stolen weight. The pressure inside builds, not gradually, but exponentially. The heat rises, the density climbs, and when the limit is crossed, there is no pause, no warning. The white dwarf ignites, not on the surface, but throughout its entire core, all at once. This is a type Ia supernova. Unlike the massive stars that explode because they've run out of fuel, these white dwarfs explode because they've taken on too much. The entire star is destroyed in seconds, its matter blasted outward in a thermonuclear detonation that leaves no core behind, no remnant, no neutron star, no black hole. Just a bright, perfect burst of light that fades over weeks. These explosions are so consistent in brightness that we use them as cosmic mile markers to measure distance across the universe. All of that, measuring the expansion of the cosmos, comes from two stars orbiting each other, from the quiet theft of matter, from a partnership no one sees. And there are other ways binary stars change one another. Sometimes both stars are massive, burning fast, destined to die young. When the first one explodes in a supernova, it leaves behind a neutron star or black hole. The system may survive. The second star, still alive, continues orbiting a remnant of what once was. Over time, it too may evolve, expand, and begin donating mass. Only now, the recipient is not another star, but something stranger, a collapsed core, a singularity. As gas falls in, it spins, heats, glows, and is devoured. The binary becomes a source of X-rays, a system of violence and transformation. Sometimes, both stars collapse. A neutron star paired with another neutron star, or a black hole with a neutron star. Their orbits shrink over time, spiraling inward. When they merge, the collision releases gravitational waves, ripples in space-time itself. We can now detect these ripples, listening to the sky for the final moments of paired stars that once circled each other in silence. But not all binaries are dramatic. Many simply orbit, affecting one another in subtle ways. They tug on each other's spin, they distort each other's shapes. Tides rise and fall on stellar surfaces. Over long periods, these effects build. Stars locked in close orbit may become synchronized, always showing the same face to one another, like dancers who never break eye contact. Even distance matters. Wide binaries, separated by thousands of astronomical units, barely influence each other at all during their lives. But when the galaxy shifts, when nearby stars pass close or gravitational tides pull on the system, those orbits can change. Some pairs are torn apart, others are nudged into tighter configurations, setting the stage for mass transfer, collision, or collapse. Binary systems are not isolated. They are part of a larger choreography, influenced by the dance of stars all around them. What begins as a pair of stars, two lights forming side by side in a collapsing cloud, can become something far stranger. A white dwarf stealing matter, a supernova born from too much love, a black hole feeding in silence, gravitational waves ringing through space. It's not just about how stars live. It's about how they live together, how proximity bends destiny, how two stars, born in the same breath of dust and light, can shape each other's ends in ways they never could alone. In the end, the fate of a star is not always written by its mass, or its temperature, or its fusion. Sometimes it is written by the presence of another, a quiet orbit, a gentle pull, a steady drift closer. And when that happens, the story of one star becomes a story of two, bound, changed, transformed. A massive star does not slip quietly into death. Its ending is sudden, violent, and breathtaking. For millions of years, it lives in a balance between gravity and pressure, burning through layer after layer of elements. Hydrogen to helium, helium to carbon, on and on until it reaches iron. And then, something changes. Fusion stops being a source of life. Iron doesn't release energy when it fuses. It only takes. In that moment, gravity begins to win. It happens faster than thought. In less than a second, the star's core collapses. The immense pressure crushes atoms until even electrons and protons are forced together into neutrons, packing matter tighter than anything else in the universe outside a black hole. The outer layers of the star, suddenly unsupported, fall inward. They crash into the stiffening core and rebound, like water slamming into rock. The energy of that rebound, coupled with the release of an immense flood of neutrinos from the collapsing core, triggers something vast. The star explodes. This is a supernova, a final act so luminous, so energetic, that it can outshine an entire galaxy. A star that took millions of years to build tears itself apart in moments. The light from the blast can travel across space for thousands, even millions of years, reaching us long after the star itself is gone. For weeks, it burns with impossible brightness, then fades, leaving behind something entirely new. In the space of that destruction, matter is transformed. The supernova doesn't just end a star, it creates the building blocks of everything that follows. Inside the furnace of the explosion, temperatures reach billions of degrees. The pressure is immense. In this crucible, atoms are slammed together with enough force to forge elements heavier than iron, gold, uranium, lead, copper. These aren't formed in the quiet burning of stars. They are born in chaos, in fire, in collapse and explosion. Every atom of precious metal on Earth, every trace of heavy element in your blood or bones, was once flung from a dying star. The calcium in your teeth, the iodine in your cells, the iron that carries oxygen in your blood. All of it came from a supernova. All of it came from death. What's left behind depends on mass. If the collapsing core is small enough, it will stabilize as a neutron star, an object so dense that a teaspoon would weigh billions of tons. If the core is more massive still, nothing can stop the collapse. It will continue until the core becomes a black hole, a point of infinite density and no return. But the explosion, the great unbinding of the star's outer layers, happens all the same. The violence sends shock waves into space, disturbing nearby gas clouds, triggering new waves of collapse. New stars are born in the wake of death, new planets, new systems, new beginnings. We've seen them, not just their remnants, but their echoes in the sky. The Crab Nebula, for example, is the ghost of a star that exploded in 1054. Ancient astronomers recorded its appearance, a sudden star in the sky that shone brightly even in daylight. Now, almost 1,000 years later, its expanding filaments of gas and dust still glow. Inside the nebula, a neutron star spins rapidly, sending pulses of radio waves across the void. A heartbeat left behind. Supernovae aren't rare, not on cosmic timescales. Somewhere in the universe, a star explodes every few seconds. Most go unnoticed from Earth, hidden behind dust or distance. But sometimes we catch them. Telescopes spot a faint dot brightening rapidly in a distant galaxy. Spectral lines shift, light curves, bloom, and fade. We watch the death of a star, light years away, delayed only by the time it takes for its last message to arrive. The information is ancient by the time we receive it, but the beauty is still immediate. And though we think of supernovae as destruction, they are perhaps the most creative force the universe has. Galaxies are seeded with heavy elements from their blasts. Planetary systems take shape in their aftermath. Even life, as we know it, requires what supernovae provide. Without them, there would be no rocky planets, no oceans, no DNA, no sentient beings to look up and wonder. It's a strange thought, to be so deeply linked to death on a scale that defies imagination. But the universe builds through cycles. Stars are not eternal. They are moments in a longer story, a process that stretches across billions of years. One star's end becomes another's beginning. Matter moves, energy changes form, and even in destruction, something is always being made. Sometimes, astronomers find the fingerprints of past supernovae in unexpected places. In the radioactive isotopes trapped in ancient rocks, in the faint glow of gamma rays sweeping through the galaxy, in the patterns of motion within star-forming clouds, and even in the isotopes layered into our atmosphere. These remnants whisper of explosions long past. They tell us that our part of space has seen death before, that Earth exists in a neighborhood shaped by stellar collapse, that we are, in some ways, living in the ashes of stars, and it's ongoing. Somewhere now, right now, a star's core is collapsing. Somewhere in the darkness, neutrinos are streaming outward, silent and unstoppable. Light is beginning its journey. Matter is becoming something new, and millions of years from now, that light may reach the surface of another world. Another observer may look up and see a point of brightness bloom where there was once only night. They won't know the star. They won't have seen it live, but they'll witness its ending. And they may marvel, just as we do, that something so violent can be so beautiful. This is the paradox of the universe. Creation through collapse, light from destruction, order emerging from chaos. We owe our existence to stars that ended themselves, to fusion that failed, to cores that gave way. And in that failure, something deeper was set free. Not just atoms, but potential. Not just debris, but legacy. Each supernova is a last breath that becomes a first word in the story of everything that comes next. Some stars die with silence, others die with fire, but a few go beyond even that. Past fire, past light, past anything we can see or measure in the usual way. These are the stars whose endings don't just mark a final moment, but tear a hole in the very fabric of space and time. For them, collapse is not an event. It's a destination. The end begins like many others. A massive star burns through its last layers of fuel, fusing heavier and heavier elements until it reaches iron. Fusion can go no further. There's no more energy to push back against the weight of its own gravity. The star's core begins to fall inward, crushed by forces it can no longer resist. At this point, a lesser star might stop at a neutron star, a sphere of matter so dense it defies intuition, its particles packed shoulder to shoulder, resisting collapse with sheer quantum pressure. But in this case, the star is too massive. The forces are too great. Even the pressure of neutrons is not enough. The collapse continues. There is no structure that can hold, no physics that can halt the implosion. And so, it falls inward without end. The mass of the core compresses beyond any familiar limit, shrinking toward a point so small and so dense that the rules we know begin to dissolve. What forms in that moment is not a star, or a planet, or any object in the traditional sense. It is a black hole, a place where gravity curves space so sharply that escape becomes impossible. Despite the name, black holes are not empty. They are not voids or tunnels or gateways. They are simply regions where mass has collapsed so tightly that its escape velocity, the speed you'd need to get away, exceeds the speed of light. And because nothing can travel faster than light, nothing can leave once it crosses a certain boundary. This edge is called the event horizon. It's not a surface in any material sense. It's a threshold, a boundary where the rules change. From the outside, you cannot see inside. Not because it's dark, but because no information can get out. No signal, no reflection, no light. Everything that falls past the event horizon is lost to us, not just visually, but causally. We cannot be affected by anything it does. It's as though the universe draws a curtain and says, "Beyond here, you cannot know." But the black hole is still there. It still has mass. It still pulls on the stars around it, bends the path of light, and tugs gently or violently at nearby space. A star in a stable orbit might circle it for billions of years, unaware how close it comes with each pass. Gas clouds may spiral inward, heating as they fall, flaring brightly before crossing the horizon and vanishing. In these moments, we see the black hole not by its own form, but by what it does to the world around it. A kind of shadow in motion, a presence made visible only by its effect. Black holes do not suck. They do not reach out and drag things into them like cosmic vacuums. If the sun were replaced with a black hole of equal mass, Earth would continue its orbit unchanged, gliding through space in the same quiet ellipse. It is only when something comes too close, too fast, too unprotected, that the fall becomes inevitable. Once you cross the horizon, there's no force you can apply, no direction you can push, no engine strong enough to take you back. Every possible future leads only deeper inside. And what happens then? We don't know, not fully, not clearly. Our physics, so powerful in so many places, breaks down at the singularity, the theoretical point at the center of the black hole, where all the mass is thought to be concentrated. Here, gravity becomes infinite, and time, as we understand it, may cease to flow. But this is not a place we can see or measure or reach. It is a consequence of equations, a ghost hidden behind the veil of the event horizon. Some theories suggest that space and time themselves are warped beyond recognition inside, that the rules of cause and effect might shift, that the geometry of the universe twists into something unrecognizable. Others suggest that quantum effects, not yet fully understood, might soften the singularity, prevent infinities, restore some semblance of order to the chaos. But these are only ideas, reaching into the dark with open hands. What we do know is this: black holes are not rare, they are not distant outliers, they are common. Ordinary stars, given enough mass and time, can become them. Our own galaxy may contain millions, and at its center, 26,000 light-years away, lurks a supermassive black hole with the mass of 4 million suns. It sits in silence, surrounded by stars whipping around it at incredible speeds, tracing invisible paths around something they can never escape. And still, it waits. There is something quiet about black holes, despite their dramatic nature. They do not blaze or burn. They do not roar or rage. They simply exist, passive yet unstoppable, altering the motion of everything nearby. They are reminders that even light can be caught, that space is not flat, that time can bend. They show us the limits of what we can see and hint at what may lie beyond those limits. Even now, as we build telescopes to detect the faint whisper of merging black holes, gravitational waves rippling through space-time itself, we are only beginning to listen, only beginning to understand what these objects mean. We can hear their collisions, feel their final moments as they spiral into one another, releasing more energy in seconds than all the stars in the universe combined. But once the merger is done, the new black hole settles, the ripples fade, and all is silent again. Perhaps that's what makes them so strange. Not the violence of their birth, or the power of their gravity, but the stillness that follows. A kind of cosmic hush, where once there was fire. Black holes are not monsters. They are not evil or hungry. They are simply the result of mass and gravity and time playing out their rules. They are stellar corpses, yes, but they are also bridges to deeper truths, places where our knowledge reaches its edge, where the laws we've trusted begin to blur. And beyond that edge, something else waits, something still hidden, something not yet known. When a star dies but doesn't vanish, when it collapses but stops just short of falling forever, what's left behind is something small and astonishing. A neutron star is the dense, compact heart of what was once a massive sun. It is the endpoint of fusion, the leftover core that refuses to disappear. The rest of the star, its outer layers, its brilliance, its shine, is blown away in a supernova. But the core, impossibly dense and stubborn, remains. It is only about 20 kilometers wide, small enough to fit within a city. You could walk across it in a few hours, if there were any surface to stand on or any way to survive. But inside that span is more mass than our entire sun. The gravity is crushing. The density defies intuition. If you could hold a single teaspoon of its matter, it would weigh more than Mount Everest. This is not a place where normal matter survives. The atoms we know, the familiar dance of protons and electrons and orbitals, are gone. Crushed under pressure, the protons and electrons merge, forming neutrons. The entire star becomes a single, gigantic nucleus, one particle pressed against another, all the way down. There's no space left in a neutron star, not in the way we understand it. No gaps, no room for molecules to breathe. Matter has been squeezed to its ultimate form. If you were somehow able to approach one, if you could survive the heat, the radiation, the gravity, you wouldn't find a glowing ball or a molten sphere. You'd find something hard, smooth, and strange. A surface that may crack like glass under stress. A crust of nuclear material resting on a fluid ocean of neutrons, with pressures so high that atoms are distorted into bizarre configurations. Beneath that, deeper still, things grow stranger, possibly forming phases of matter that have never existed anywhere else. And yet, these stars live. Not in the burning sense, not in the glowing and fusing and warming sort of way, but in motion, in rotation. Some neutron stars spin so fast they complete hundreds of rotations every second. These pulsars, as we call them, emit beams of radiation from their poles. Like cosmic lighthouses, they sweep their beams across the sky, and if Earth lies in their path, we detect them as regular pulses, precise, steady, predictable to the microsecond. Timekeepers forged from death. The spin comes from the conservation of angular momentum. As the dying star collapses, its rotation speeds up, like a figure skater pulling in their arms. A slow spinning giant becomes a fast spinning remnant. And because these stars are so dense, they don't slow down easily. They continue to spin for millions of years, gradually losing energy, gradually dimming, but persisting long after their parent star is gone. And though they are small, they are not weak. Neutron stars have magnetic fields that can be 1 trillion times stronger than Earth's. In some, these fields twist and shift, storing immense tension. When the stress becomes too great, the crust can crack in a starquake, releasing bursts of energy more powerful than anything else in the galaxy. These magnetars, as they're known, are among the most violent objects in the cosmos, not because of their size, but because of what they hold within. And yet, they are quiet in a way that is hard to describe. A neutron star doesn't shine like its former self. It doesn't blaze across the sky. Most are invisible to the naked eye, their heat cooling slowly over time. They don't call attention to themselves unless something happens. An orbiting companion, a collision, an outburst. Otherwise, they drift through space like ghosts, city-sized memories of stars that once warmed solar systems. We know them through their effects, the radiation they emit, the ripples they send through the cosmos when they merge, the subtle shifts in timing when their pulses reach us. In recent years, we've begun to detect their mergers, two neutron stars spiraling into each other, crashing together in an event so powerful it warps space-time itself. These collisions are not just violent, they're generative. They produce gravitational waves we can now hear. They forge heavy elements in vast quantities: gold, platinum, rare atoms scattered into space, a ring, a necklace, a signal. It is strange to think that these tiny remnants, these small dense stars, are among the most powerful engines of change in the universe. They begin as endings, as the core that could not fuse, could not shine, could not hold back collapse, and yet they persist. They wait, they turn, they pulse in rhythm with the heartbeat of a broken cosmos, holding together what remains. And sometimes they challenge even our best theories. Some neutron stars may spin too fast. Some may have masses that stretch the boundary between neutron star and black hole, skimming the edge of what's possible. Others may harbor exotic forms of matter, quark soup, strange particles, condensates that exist only at pressures we cannot replicate. They are, in many ways, laboratories, compressed into the sky, locked away in the cold and the quiet, but still humming with possibility. The space around a neutron star is often empty, cleared by the violence of its birth. And so it travels through darkness, through silence, a solitary monument to what once was and to what might still be. Because even in their quiet, neutron stars are not finished. They evolve. They collide. They decay. They wait for the touch of another star, the approach of a companion, the final convergence that might trigger something new. And in this waiting, there is grace. The grace of endurance. The grace of pressure and spin and mass held in balance for eons. These stars are reminders that small things can carry great weight, that endings are not always empty, that what remains after collapse may be more lasting than what came before. The night sky holds many wonders, but if you could look closely, if you could see past the light and into the dark, you might find one of these city-sized suns drifting alone, spinning quietly, pulsing like a heartbeat left behind. Not a star in the usual sense, but something deeper, denser, stranger. A star that burned, collapsed, and never quite let go. Stars are not fixed. They are not still. Though they may seem eternal, hung motionless in the sky, they are always moving, always changing. They live on borrowed time, consuming fuel, shifting in shape and size as they age. And when the balance they've held for billions of years begins to falter, their bodies respond, not with silence, but with growth. They swell, they inflate, they expand outward, layer by layer, until the space around them becomes theirs. In this slow but inevitable swelling, stars become giants, red giants. In the case of stars like our own sun, their outer envelopes grow vast and loose, 100 times wider than before, reaching outward with arms made not of fire, but of hot, churning plasma. And in this reaching, they change the architecture of their solar systems. They warm what was once cold. They brighten what was once dim. And they begin to threaten what once orbited safely. Because when a star becomes a giant, it does not stop for its planets. It does not ask permission to grow. It does not pause at the edge of their orbits. It continues, reaching past the boundaries it held for eons. Mercury, closest to the sun, has no chance. Its orbit is too tight, its days too short, its distance too small. As the sun expands, Mercury will be overtaken, not in an instant, but in a slow unfolding embrace. The heat will rise. First, the surface will melt, then boil, then become a haze of vapor and ash. Then, the atmosphere, if any remains, will be stripped away. Finally, the planet itself will be swallowed whole, folded into the outer atmosphere of its parent star. Venus may follow, Earth could be close behind, but engulfment is not always that simple. Some planets do not simply fall into their stars like stones dropped in water. As the star expands, it begins to lose mass through solar wind, and its gravity weakens slightly. At the same time, tidal interactions pull at the planets, slowing them down, warping their orbits, twisting their trajectories. In some cases, this delicate dance causes the planet to spiral inward, drawn closer with each passing revolution. In others, it might drift outward, pulled by the very momentum that once kept it safe. But if the inward spiral begins, the outcome is rarely peaceful. The planet begins to fall, not in a plunge, but in a slow, spiraling descent. And long before it meets the star's surface, it begins to die. The tidal forces acting upon it stretch and squeeze, distorting the shape of the world, heating its interior through friction. Crusts crack, oceans boil, the surface may be ripped apart before it even touches the star itself. The result is a tidal disruption, a destruction by gravity, a kind of slow tearing that erases not only the planet's form, but its history. We've seen signs of this happening around other stars. Through the haze of distant light, we observe dimming patterns that suggest planets being broken apart. We see clouds of debris, odd chemical signatures, hints of planetary material swirling inside stars that should have none. These are not guesses, they are traces, echoes of planetary deaths witnessed across vast distances. Even the remnants of devoured worlds can sometimes remain in orbit, a shredded disk of rock and dust and metal circling the ghost of what was. In white dwarf systems, where the star has already 22, shed its outer layers and collapsed into a dense core. We've detected rings of debris that can only come from shattered planets, a legacy not of life, but of loss, a record written in fragments and ash. And yet, there is no malice in any of this. Stars do not intend to destroy. They do not choose to consume. They simply follow the script of physics. When their core runs low on hydrogen, they fuse helium. When helium runs low, they climb the ladder of elements. Each new layer requires a higher temperature, a larger size. Expansion is not a whim. It is a necessity, a consequence of staying alive just a little longer. In that process, they shed much of themselves. A red giant is a leaky, unstable thing. It loses mass constantly, its outer layers drifting away into space, forming glowing shells of gas and dust. This shedding of skin is gentle compared to the violence of a supernova, but no less dramatic in its scale. Over time, the star's gravity can no longer hold what it once did. Orbits shift, the balance tilts, and the inner planets, if they haven't already been swallowed, may be set adrift. Even Earth, if it somehow escapes engulfment, will not remain the same. The sun's heat will rise long before its outer edge reaches us. Oceans will evaporate, the atmosphere will be stripped, the surface will bake and blister. Long before our world is taken, it will be made unrecognizable. But not every world dies in silence. Some fight back in ways we can barely imagine. There is a class of stars known as hot Jupiters, gas giants that orbit their stars far too closely. Some of them may have migrated inward after formation, moving through the gravitational field of their system, sliding toward their suns. In these extreme cases, the heat from the star can strip away the outer layers of the planet, creating a trail of gas and ions that stream out behind it like a comet. These planets are being digested slowly, their atmospheres peeled off by stellar heat, their cores exposed inch by inch. Eventually, even these may be gone, and so the cosmos moves forward, patient and inevitable. The lives of planets are long, but not infinite. The fates of worlds are not solely their own. They are tied to the stars they orbit, drawn into a gravitational story that ends, more often than not, in surrender. Whether torn by tides or swallowed by heat, whether shredded into dust or melted into plasma, planets can die. Not from collision or war or decay, but from the quiet, relentless growth of the thing they depend on most. A star. The same star that once warmed them, lit them, gave them everything they needed, may one day stretch out its arms and take it all back. A star does not need to explode to lose itself. It can do it slowly, persistently, breath by breath. In the vast silence of space, stars shed their layers, not in screams, but in winds. Outflows of particles and energy that push outward in all directions. These stellar winds are not like the winds we know on Earth. There is no air, no breeze, no fluttering of leaves. Instead, they are floods of charged particles, racing away from the star at millions of kilometers per hour, invisible but devastating. They carry not just energy, but substance, mass. They carry the star itself. Some of the most massive stars in the universe lose more than half their mass this way. They are born immense, but that largeness is unstable, difficult to hold on to. Their fusion burns fast and hot, creating light so intense it pushes against their own gravity. That light exerts pressure, radiation pressure, on the surrounding plasma, and when it is strong enough, it lifts material from the surface and flings it into space. Over time, this becomes a wind, not a gust, but a storm, a constant stream of matter being ejected into the cosmos, thinning the outer layers of the star, peeling it down like the skin of a fruit. These winds reshape everything around them. As the star sheds mass, it changes the space nearby. The outflowing particles crash into the surrounding gas and dust, compressing some regions, dispersing others. They can sculpt nebulae into arcs and filaments and bow shocks, shapes that seem like art, but are really records of motion and force. The interstellar medium, that thin mist of material that floats between stars, is stirred by these winds, seeded with heavier elements, enriched with debris. Long before a star dies in a supernova, it has already begun giving itself away. Some of the most dramatic examples are the Wolf-Rayet stars. These are the stripped-down remnants of massive stars that have lost their outer hydrogen layers entirely, revealing the blazing cores beneath. They are fierce and short-lived, radiating with an intensity that defies distance. Their winds are among the strongest in the universe, dense, fast, relentless. You can think of them as stars laid bare, no longer cloaked in softness, no longer cushioned by cooler outer layers, just the burning engine exposed, spinning and shedding and pushing itself apart. What remains is not stable. The more mass a star loses, the harder it becomes to maintain equilibrium. Gravity weakens, fusion shifts. Some stars collapse before they can explode. Others live a little longer, trembling on the edge of balance, suspended between implosion and eruption. A Wolf-Rayet star may burn for only a few 100,000 years in this state. Nothing compared to the billions of years other stars enjoy. But in that short time, it changes everything around it. Not just with light, but with force. The winds themselves are not uniform. They can come in pulses, in waves, in steady streams or sudden bursts. Sometimes a star ejects a shell of material all at once. A pulse of loss that expands outward like the rings of a ripple in water. Other times, the wind flows more gently, continuously bleeding matter into space. The difference is often determined by temperature, rotation, magnetic fields, and even the composition of the star's outer layers. Every wind is a kind of fingerprint, a signature, a silent record of the star's inner workings, and there are consequences. As a star sheds mass, its future shifts. Its core remains, still fusing, still driving the machine forward. But with less mass pressing inward, the fusion changes. Some stars that might have ended in supernovae instead fizzle into white dwarfs. Others explode sooner than expected, their internal balance disrupted by the loss. Mass is not just a measure of size, it's a prophecy. It tells us what a star can become, and when that mass is lost, the prophecy rewrites itself. Even our sun loses mass through a solar wind, gentle by cosmic standards, but persistent. Every second, it sheds about 1.5 million tons of material into space. Most of it flows outward quietly, without drama, without heat. But during solar storms and flares, the wind surges, charged particles hurling toward the planets, disturbing magnetospheres, painting auroras in the sky. It is a reminder that even calm stars exhale. Even the quietest light has a voice. But with the massive stars, the voice becomes a roar. A single Wolf-Rayet star can lose the equivalent of Earth's entire mass every year. That loss pours outward, not only altering the star's destiny, but shaping its surroundings for light years. Nebulae, like the Crescent Nebula in Cygnus, are carved from the winds of such stars, their arcs and folds telling the story of a core laid bare. These winds are not accidents. They are not side effects. They are part of the life cycle, part of the rhythm. And so, in the quiet reaches of space, far from sound and motion, a star becomes its own undoing, not through explosion, not through collapse, but through breath. It sheds its layers in radiant silence, revealing what lies beneath. It gives to the universe not only light, but matter. Hydrogen becomes helium. Helium becomes carbon. Carbon becomes wind. And that wind becomes dust. And that dust becomes worlds. By the time the star finally reaches the end, whether in flame or fade, much of what it was has already been scattered, sent outward in streams of plasma and atoms, seeded into the galaxy, laid down in the bones of future stars and planets. Even you, sitting here, listening in the dark, carry pieces of those ancient winds, calcium in your bones, iron in your blood, oxygen in your breath. You are not separate from the stars. You are what they let go of, what they gave up in the slow, shimmering act of shedding themselves bare. Not all endings shout with the same voice. In the universe, even destruction comes in variety, layered, precise, sometimes delicate, sometimes deafening. Supernovae are often thought of as singular events, stars blowing apart in a final blaze of glory. But the truth is far more nuanced. These are not uniform flashes of light. They are a spectrum of unravelings, each shaped by the star that came before and the circumstances that push it to its end. The label supernova contains multitudes, different engines of collapse, different triggers, different consequences. Some supernovae arrive suddenly, without a partner, a consequence of a massive star running out of fuel. Type 2 supernovae come from these solitary giants. For millions of years, the star fuses lighter elements into heavier ones, stacking its core like layers of a furnace. Eventually, it hits iron, an element that cannot be fused for energy. The core becomes inert. Gravity, unopposed, takes hold. In less than a second, the core collapses. Neutrons are crushed into existence. The outer layers, no longer supported, crash inward and rebound in a chaotic eruption. The result is a luminous death, bright enough to outshine an entire galaxy for a short time. What remains may be a neutron star, or, if the core was massive enough, a black hole. But not all stars can end alone. Some need a partner to die. Type Ia supernovae are among the most precise explosions in the cosmos. They come from white dwarfs, stellar remnants that have already burned out their fusion engines, left to cool in silence. But if a white dwarf lives in a binary system, it may slowly siphon material from its companion. A steady trickle of hydrogen or helium accumulates on its surface, adding mass grain by grain. There's a limit to how much a white dwarf can bear. When it reaches about 1.4 times the mass of our Sun, a value known as the Chandrasekhar limit, it can no longer support its own weight. Fusion reignites suddenly, not in the core, but throughout the entire star at once. It doesn't collapse, it detonates. Unlike core collapse supernovae, type Ia explosions leave no remnant behind. The star is entirely destroyed, vaporized into heavy elements, and scattered into the void. These explosions are so consistent in brightness that astronomers use them to measure cosmic distances. They are cosmic lighthouses, lighting up the expanding fabric of space, letting us trace the acceleration of the universe itself. But their reliability masks a truth. They only happen under very specific conditions. A precise amount of mass, a binary companion, a delicate balance that, once broken, erases the star completely. Then there are the monsters. Pair instability supernovae occur in stars so massive, so heavy with fuel, that the very fabric of light begins to shift. Deep in the cores of these stars, the photons themselves become unstable. Instead of simply bouncing around and supporting the star with pressure, they begin to convert into matter. Electron-positron pairs that do not resist gravity in the same way. This sudden loss of photon pressure causes the core to contract violently. Fusion races ahead, trying to compensate, burning through oxygen and silicon in moments. The result is not collapse, it's annihilation. There is no neutron star, no black hole, just energy and debris. The star ceases to exist, its mass transformed into an expanding shell of elements and radiation. It leaves behind nothing but space, and the memory of an explosion so powerful it can seed star formation in distant regions of the galaxy. These are rare, ancient, perhaps more common in the early universe, when the first stars were larger and wilder, unpolluted by the metals that now temper their growth. Each type of supernova sculpts the universe in its own way. The elements we find in planets, in bones, in oceans, come from these cataclysms. Iron and nickel from core collapse events, carbon and silicon from pair instability behemoths, the oxygen we breathe, the calcium in our teeth, the gold in wedding bands. None of it formed in the calm warmth of a living star. All of it came from endings, from eruptions that tore stars apart and flung their contents into the void. Even galaxies themselves bear the fingerprints of these explosions. Supernovae stir the gas between stars, shock it into collapse, trigger waves of new star formation. Their energy pushes and pulls, heats and compresses. Over time, this shaping force influences where stars can form, how long gas clouds linger, whether planets will have the ingredients for life. Supernovae are not just conclusions, they are beginnings too. Reset buttons, fertilizers, alchemists of the cosmos. And yet, they remain hard to predict. We know which stars are likely to end this way, but we cannot say exactly when. A massive star might live 10 million years, but its final day arrives in a heartbeat. From the outside, it may look unchanged, shining brightly, seemingly stable, until the core gives in and the star disappears in an instant. Sometimes all that's left is a shock wave, a nebula, a ghost of light echoing through space. It's humbling, this range of endings, to know that stars do not simply flicker out, that some vanish quietly, and others erupt with such violence that their echoes can be seen for centuries. The Chinese astronomers who recorded a bright new star in the sky in 1054 had no idea they were witnessing a supernova. The light they saw marked the death of a star 6,500 light-years away. Its remnants still glow today as the Crab Nebula, a tangle of expanding dust and gas wrapped around a neutron star that spins 30 times per second. That's the legacy of supernovae. Not just light, but structure. Not just chaos, but clarity. They offer us clues about stellar evolution, galactic history, even cosmic expansion, and each type adds another piece to the puzzle. Type 2, fueled by core collapse. Type Ia, born from companionship and quiet theft. Pair instability, ending in total destruction. Some explosions leave seeds, others leave silence. But all of them leave something. Even when the star is gone, there's a quiet kind of almost in the universe, a nearly, a not quite. It lives in the space between what could be and what is, in the silent stories that never grew loud. Brown dwarfs are that silence, born the way stars are, inside collapsing clouds of gas and dust. They gather mass, form cores, begin to heat. They do everything right, until they don't. Because there's a line in the cosmos, a threshold where mass becomes destiny. To become a true star, to ignite the long fire of hydrogen fusion, an object must be heavy enough, about 75 times the mass of Jupiter. Many don't make it. They come close, but fall just short. Brown dwarfs are the almost stars, too big to be planets, too small to be stars, trapped in between. Their cores press inward as gravity tries to compress them. Heat builds, but not enough. Not enough pressure, not enough weight, not enough of the brutal squeeze needed to force hydrogen atoms to fuse into helium. They do manage some fusion at first, of deuterium, a heavier form of hydrogen, or sometimes lithium. But it doesn't last. It's a flicker, a spark that burns out early, and then they cool. Still, they glow. Not with fire, but with heat. Their surfaces are warm, sometimes, thousands of degrees, but without the sustained brightness of stars. They shine in infrared, in wavelengths the human eye can't see. If one passed nearby in space, we might never notice it without the help of telescopes tuned to those deep colors. They slip past the edge of visibility, their glow more of a whisper than a beacon. Some brown dwarfs form in clusters, born alongside true stars in the same stellar nursery. Others are ejected during early gravitational chaos, flung into the dark on lonely trajectories. They can drift for billions of years, orbiting nothing, companionless, invisible. Without the weight to light up, and without the anchor of a sun to orbit, they become wanderers, ghosts, solitary failures by the coldest definition of success. And yet, failure doesn't feel like the right word, because there's something strangely persistent about brown dwarfs. Their heat takes a long time to fade. Even though they don't burn in the way stars do, their interiors remain warm for billions of years. They cool slowly, inexorably, radiating their energy into the void. Some of the older ones are now barely warmer than planets. Their light is gone, but their mass still warps space. They still exist, unchanged, unburned. No one's sure how many there are. They're hard to detect, hiding in the galactic shadows. For every star we see, there could be dozens, maybe hundreds, of brown dwarfs moving unseen. A hidden population of almosts, shaped like stars, dim as dusk. Some estimates suggest they may outnumber stars. If true, it means the majority of stellar births fail to reach ignition. The universe is not a place of perfect outcomes. It is a place of attempts. Some brown dwarfs blur the line even further, skimming just below the fusion threshold. These objects may shine faintly for a time, teetering on the edge of stardom before gravity lets go and cooling wins. Others are smaller, colder, barely glowing at all. They come in classes, L, T, Y, grouped, not by light, but by temperature and chemistry, a language built around what isn't seen. Some have atmospheres of clouds and storms. Some may rain iron or silicates. Some spin with hurricane-like speeds. But all of them move quietly, their stories mostly undetected. And yet, they matter. In the gentle gravitational tug they exert on nearby objects, in the way their presence reshapes planetary systems, in their utility as laboratories for understanding both stars and planets. Brown dwarfs are clues, filling in the gradient between things we thought were distinct. They show us that categories bend, that boundaries blur, that not everything fits neatly into the boxes we draw. They also challenge our sense of drama. In a cosmos full of explosions, bursts, and dazzling brilliance, brown dwarfs are subtle. They don't go supernova. They don't collapse into black holes. They don't light up the night sky. But they endure. Long after massive stars have flared and died, brown dwarfs will still be here, cooling, drifting, undone, but unbroken. Their longevity is a kind of quiet defiance. They are reminders that the universe doesn't just celebrate the brilliant. It contains the faint, the failed, the almost there. The things that didn't quite make it but still exist anyway, still exert influence, still matter. Not all stars are born to shine. Some are born to wait, to glow in wavelengths we can't see, to shape the dark rather than pierce it. And maybe, in their silence, there is a kind of grace, a humility written into their physics. They ask nothing. They make no demands on the cosmos. They simply are. Soft echoes of ambition, cooling slowly in the cold between stars. They are the dreams that didn't catch fire, but refused to disappear. In the end, perhaps the measure of a thing isn't only in its light. Maybe it's in its persistence, its shape, its silent orbit. Maybe the story of a brown dwarf isn't about what it failed to become, but what it quietly became instead. Not all stars are meant to shine. Some are meant to endure. Some stars don't burn with a steady flame. They breathe, expand, contract, expand again. Their light pulses across the dark like a slow heartbeat, not constant but alive. These are the variable stars, celestial bodies whose brightness changes over time, not because of clouds or shadows or orbits, but because of something deep within them. They are unstable in the most elegant way. Their outer layers swell and fall. Their temperatures rise and fall. Their light brightens and dims in repeating patterns that span hours, days, or weeks. From afar, it can feel like a kind of flickering, but up close, if one could ever be close, it would feel like standing next to a breathing giant. The pulses are not random. They are consistent, even predictable, like a metronome for the universe. The physics behind them lies in the balance between gravity pulling in and pressure pushing out. Deep inside, heat builds, causing the star to expand. But as it stretches, the outer layers cool and become more opaque, trapping energy that pushes back. The cycle reverses, the star contracts, pressure builds again, and the expansion starts anew. This rhythmic dance produces light curves, beautiful arching records of luminosity over time. Among the most famous are Cepheid variables. These stars are not just beautiful, they're useful. Their periods of brightness are directly related to their intrinsic luminosity. That means by measuring how quickly they pulse, astronomers can determine how bright they really are, and then, by comparing that to how bright they appear from Earth, calculate how far away they must be. Cepheids are like cosmic lighthouses, steady and dependable, marking distances across the universe. It's because of them that we first mapped the size of our galaxy, then realized there were galaxies beyond our own, and eventually measured the expansion rate of the universe itself. Their role in the history of astronomy is enormous. It was Henrietta Swan Leavitt, studying Cepheid variables in the Magellanic Clouds in the early 1900s, who first discovered the period luminosity relationship. That quiet revelation opened the door to a new kind of measurement, a ruler made of stars, not sticks. Decades later, Edwin Hubble used Cepheids to prove that the Andromeda Nebula was actually a separate galaxy, far beyond the Milky Way. A flickering star, pulsing on a distant night, changed our understanding of everything. Other variable stars, like RR Lyrae, also serve as tools for navigation. These stars are older and fainter than Cepheids, but they too pulse with reliable rhythm. found mostly in the globular clusters that surround the galactic core. RR Lyrae stars help chart the shape of our galaxy's halo. They are ancient, fossils of the early universe, and their pulses are a kind of heartbeat from the past. Every flicker tells a story not only of distance, but of age, composition, and galactic motion. Not all variables are the same. Some are large and luminous, others small and faint. Some pulse rapidly, others slowly. There are stars whose variability is driven by internal processes, and others whose changes come from external forces. Eclipsing binaries, rotating stars with dark spots, or systems where matter is exchanged between companions. But the pulsating variables, those that swell and contract on their own, are among the most mesmerizing. They turn physics into poetry. They turn data into rhythm. To observe one is to wait. Night after night, astronomers track their light, watching as it waxes and wanes. It's a patient kind of study, one that rewards those who look not for sudden bursts, but for subtle changes. In classrooms and observatories around the world, students learn to read these patterns, to extract meaning from motion, to feel time written in the brightness of a star. Even their silence feels communicative. There's no sound in a vacuum of space. But if you could hear a Cepheid pulse, it might sound like a slow drum, deep and echoing, each beat marking the passing of days. Not chaotic, not wild, just steady, endlessly repeating. A reminder that the universe has rhythm, even in its emptiest corners. Some of the most dramatic pulsators, like Mira variables, go from nearly invisible to brightly shining in the span of months, only to fade again. These stars are dying, red giants near the ends of their lives. Their outer layers swell enormously, then fall back in, like lungs trying to remember how to breathe. Their variability is more chaotic, but still patterned, like waves with strange currents underneath. Observing them feels less like watching a machine and more like watching a body. And maybe that's why these stars hold our attention. They mimic life. They pulse like hearts. They move like breath. They change, just as we change. Their light is not fixed. It is not perfect. It is dynamic. That imperfection draws us in, because in a sky full of steady stars, the ones that flicker feel the most alive. We often think of stars as eternal, burning unchangingly for billions of years. But variable stars remind us that even stars have moods. Even they swell and shrink, glow and fade, rise and fall. They have rhythms, and those rhythms tell us secrets about distance, about time, about what it means to burn without burning out. And perhaps most hauntingly, they do all of this without ever knowing we're watching. They pulse not for us, but because that is what they are. Their rhythm is not performance, it is truth. Gravity, heat, and time shaping light into patterns. And we, lucky enough to notice, get to listen, to measure, to wonder. In their flicker, we find constancy. In their change, we find tools. And in their silence, we find song. They're not planets, not even close, though the name remains like a smudge from an older telescope, a guess etched into history. Planetary nebulae are not worlds, but the last outward breath of dying stars, released into the dark in a final, luminous gesture. The name comes from the way they first appeared in early telescopes, faint, round, disc-like shapes that resemble distant planets to the eye of the observer. But what they truly are is something stranger, more ephemeral, ghostly. A planetary nebula begins when a star like our Sun, gentle in its fusion and modest in its mass, reaches the end of its long, stable life. For billions of years, it has quietly fused hydrogen into helium, warming nearby planets and sending light outward in all directions. But hydrogen doesn't last forever. When the fuel at the core runs out, the balance breaks. Gravity pulls inward, pressure fights back. The outer layers swell, The red giant phase is a kind of death rattle in slow motion. The star balloons outward, its atmosphere expanding into space, unstable and unmoored. Eventually, it begins to shed these outer layers in pulses and waves. What's left behind is a hot, dense core, white and brilliant and dying. And surrounding it, an envelope of gas and dust lit from within, like fog catching the light of a passing car. That glow, that drifting, glowing shell, is the planetary nebula. They don't last long. A cosmic blink, just 10 to 20,000 years before the nebula disperses and fades into the interstellar medium. But in that short time, they can be stunning. Shapes emerge in the dust. Symmetrical rings, hourglass figures, twin-lobed wings that stretch like butterfly wings caught mid-beat. Some look like eyes, wide and watchful. Others resemble smoke rings or radiant halos. Their symmetry is often unsettling, too perfect, too intricate, as though shaped by invisible hands. And maybe they are, in a way. The symmetry often comes from hidden companions, binary stars, orbiting close enough to stir the outflow into spirals and lobes, or from magnetic fields, gently sculpting the material as it escapes, or from rotation, flinging mass outward in preferred directions. The exact mechanics aren't always known. The nebula forms where precision meets mystery. The colors are not imagined. They come from the atoms themselves. Oxygen glows green, hydrogen, red, helium, blue. Ultraviolet light from the central white dwarf ionizes the gas, causing it to emit at specific wavelengths. It's a kind of stellar fluorescence, a chemical ghost story told in hues and halos. Images captured by telescopes, especially the Hubble Space Telescope, show planetary nebulae as intricate paintings in deep space. Structures so delicate and precise they appear designed, but so wild in their variety that no two are ever alike. The ring nebula, the helix, the cat's eye, the butterfly. Each one a different version of the same story. A star reaching the end of its ability to hold itself together, and instead choosing to let go. And someday, our sun will do this too. Not soon. Not in our time, or in the time of anything we've built or imagined. But in about 5 billion years, give or take, the sun will enter its red giant phase. It will swell, possibly engulfing the inner planets, including Mercury and Venus. Earth may be scorched beyond recognition. Then, it will begin to cast off its outer layers in waves, gently, as if exhaling, until all that remains is a white dwarf surrounded by a luminous cloud of gas, our planetary nebula. There is something poetic in the idea that the sun, so constant in our sky, will one day become a ghost, that after everything it illuminated, it will leave behind not silence, but light, not absence, but a structure, beautiful, symmetrical, and brief. Planetary nebula are not just endings, they're transformations. The material expelled will mix back into the galaxy, seeding future stars and planets with heavy elements forged in the heart of the dying star. What looks like loss is, in fact, a gift, a return, a rejoining of the cycle. Some of the atoms in your body may once have passed through such a nebula, breathed out from a dying star, traveled across eons, and gathered again into something thinking and warm. There's a strange comfort in that, a quiet link between flesh and gas, between heartbeat and starlight, and the white dwarf left behind. Small, dense, cooling, will remain long after the nebula fades. For billions of years it will glow, shedding its residual heat like a banked ember, silent, enduring, and nearly invisible, a core that refused to die. Sometimes, when you look at the images of these nebulae, those astonishing shapes framed against a field of stars, it's hard to believe they're real. They look painted, stylized, too vivid to be natural. But they are. They're the remains of stars not so different from our own, and they're fragile, not just in duration, but in structure. A nebula can be disrupted by a passing star or by its own instability. It's a sculpture in smoke and ionization, frozen only briefly in time, yet we see them. Across thousands of light years, their light reaches us, echoes of death, shining long after the moment has passed. Silent, intricate remnants drifting through space, bearing witness to a transformation we will never hear, never feel, but can still see. Planetary nebulae are proof that endings can be beautiful, that fading away is not always silent, that in the moment of surrender, stars do not disappear. They bloom. They say stars die, and most do. They collapse inward, scatter outward, cool down, fade. Some explode in radiant final acts, some shrink into silence. But in the quiet margins of galaxies and the crowded bustle of star clusters, there are strange stories that don't follow the rules. Endings that forget to stay endings. Remnants that stir, merge, collide, and shine again. Because even in the stillness of what's left behind, the universe sometimes stirs the ashes. White dwarfs, those silent cores left from long-dead stars, are supposed to fade. They're the bones of suns, no fusion, no fire, just heat, slowly bleeding away into the black. But if two drift close enough, circling each other like dancers in a doomed waltz, gravity begins to pull. They spiral in, closer, faster. The orbit shrinks over millions of years until the final embrace becomes violent, and two failed stars become something new. Sometimes, when the mass is just right, the impact reignites fusion. The dead burn again, not in the old way, slow and stable, but suddenly, completely. A flash, a burst of light that can rival the brilliance of a whole galaxy. This is not resurrection in a gentle sense. It's chaotic, explosive. But in that destruction is new light, a kind of rebirth carved from collision. The boundaries between life and death blur, and matter once thought spent begins to glow. And elsewhere, in the crowded neighborhoods of globular clusters, where stars are packed so densely their gravitational fields begin to tug at one another, there are anomalies. Stars that shine too brightly, too blue, too young to make sense among their aging neighbors. These are the blue stragglers. Their name comes from how they appear, lagging behind in a population of older stars, still burning with youthful heat. But they are not young. They are remade. One theory suggests that blue stragglers form when two stars collide and merge, combining their mass into a single, hotter core. Another posits a quieter method, mass transfer in a binary system, where one star siphons material from another, growing fat and hot, while its companion shrinks. Either way, the result is the same. A star that should be slowing down instead runs again. It is not starting over, it is continuing, a second chance wrapped in gravity and heat. Galaxies, too, are not beyond this recycling. The interstellar medium, the gas and dust expelled from dead stars, from supernovae, from the slow winds of red giants, becomes the raw material for new stars. It drifts through space, drawn into clouds, cooled by shadow, stirred by motion. A passing shockwave, a nearby supernova, or the pull of gravity from a spiral arm can cause the gas to collapse again. And from that collapse, a new star is born. This cycle of death and rebirth is the hidden pulse of the cosmos. It is not neat, not always symmetrical, but it is relentless. The atoms forged in the hearts of ancient stars, some of them long gone, find their way into new ones. Hydrogen, helium, carbon, iron, flung into space, gathered again, compressed, heated, ignited. The stars we see now are not only themselves, they are the memory of those that came before, and some stars are reborn not by fusion, but by us. When we point telescopes into deep space and catch the light from galaxies so far away that we see them as they were billions of years ago, we give those stars a second kind of life. Their light has crossed unimaginable distances and times to reach us. And when it touches a detector, when it's recorded, seen, interpreted, it lives again, just for a moment, in the mind that receives it. Even starlight gets to be remembered. Not every star gets a second life. Most don't. But enough do that we can say this much. Death is not the only ending written into the sky. There are systems where everything should be over and isn't, where fragments come together again, where gravity and chance conspire not just to destroy, but to restart. It doesn't always make sense. Why would a universe built on entropy and expansion allow for this kind of persistence? Why would it let the dead shine again? But maybe the rules themselves are broader than we think. Maybe time, distance, mass, and heat all have places where they bend, where they make room for loops and returns. In that space, rebirth becomes possible, not just for stars, not just for systems and clusters and clouds, but for us too. We, who are made of their dust, pulled together in the gravity of our own stories. We burn, we fade, we break. And sometimes, in unexpected collisions or quiet accumulations, we begin again. A white dwarf does not know it will become a nova. A pair of stars doesn't know it will merge. A cloud doesn't know it holds the seed of a sun. And we don't always know what waits inside the things we've left behind. But the universe does. And every now and then, it reaches back into its vault of remnants and says, "Not yet, not quite. Let there be light." When a star dies in a supernova, it does not vanish quietly. The explosion is swift, immense, and luminous, but its story is not over when the flash fades. Some deaths leave marks carved into the fabric of space, echoes stretched across time. Not metaphorical ones, actual, visible echoes. The light from a supernova doesn't simply radiate outward and disappear. It reflects, it scatters, it rebounds from the dust that drifts like ancient fog through the galaxy. And when it does, it tells its story again. These are called light echoes, not illusions, not tricks, but the delayed memory of brightness. The light from the original blast races ahead, moving in all directions, but some of it takes the long way around. It strikes a wall of interstellar dust, a silent, dark structure that's been floating unobserved for millennia, and bounces toward Earth. When it arrives, it carries a replay of the explosion, like hearing thunder after lightning, only stretched not by seconds but by centuries. We've seen these echoes. From Earth, through telescopes tuned with precision and patience, astronomers have watched them unfold, ripples of old light shimmering on the dust of distant space, flickering like a campfire's reflection on cave walls. In some cases, we've seen supernovae that took place long ago, long before the age of photography, and reconstructed their light by catching these reflections. We watched a ghost of a star die centuries late, and still, it was brilliant. There's something haunting in that, the idea that the death of a star is not a moment, but a series of remembered flashes. That even if no one was looking the first time, the universe preserves a record. That light, even old light, doesn't forget its origin. And it isn't just light that carries a supernova's story. In 1987, a star died in a nearby galaxy, the Large Magellanic Cloud, and for the first time in history, humans detected something before we saw it. Beneath the mountains of Japan, inside a vast underground chamber of water and silence, a detector named Kamiokande picked up a whisper from the explosion. Not light, not sound, neutrinos. These particles are nearly massless, almost untouchable, able to pass through entire planets without slowing down. And yet, for a supernova, they are the first messengers. As the core collapses, it floods the universe with neutrinos, ghost particles, released in numbers too large to grasp. They stream out at nearly the speed of light, faster than the blast wave can force its way through the layers of the star. So they arrive first, and for a few quiet moments before the light reached our eyes, The Earth was bathed in a silent storm of neutrinos. We didn't know it then. Not until the telescopes caught the burst and turned their gaze. But when scientists went back and checked the timing, there it was. Those delicate ripples in the detector, a record of the universe clearing its throat before the shout. The supernova was called SN 1987 amperes, and we still see its aftermath expanding today. A growing ring of gas and light pushed outward by the force of death, lit by the radiation that lingers in the wreckage. It has changed shape and color over the decades, and we watch it like we might watch the slow unfurling of a scar. It doesn't fade quickly. It persists, like all things left behind in space. The echoes of supernovae take many forms. Some are light bouncing off dust. Some are particles we almost miss. Some are shock waves moving through space, compressing clouds, waking up new stars. Because death in the cosmos is not isolated. It has influence. The shock of one star's end might trigger the beginning of another. It might set in motion new collisions or push raw material into the gravitational hands of a forming system. In this way, the death of one star might echo through others, even black holes. Those ultimate ends are echoes. When a supernova collapses into a black hole, it leaves behind not just absence, but gravity. It bends the paths of stars that come near. It emits gravitational waves if it collides or consumes. These too are echoes, felt not as light or sound, but as ripples in the fabric of space-time itself. We have instruments now that can feel those ripples, and when they do, they tell us that something massive, something irreversible, has happened far away. The universe doesn't always speak in bursts. Sometimes it whispers over long distances, and sometimes it waits. Some supernovae leave behind no light, no neutron star, no echo we can see. But we think they happened. We see stars that should still be there, and they're gone, disappeared without a trace. These are called failed supernovae, where the core collapses and falls inward entirely, forming a black hole without fanfare, no bright burst, no lingering glow. But even these leave a hole in the sky, a gap where once there was light. The absence becomes the message. We call them echoes, but really they are memories. The universe is full of them. Some are bright, some are faint, some travel billions of years to find us. Some arrive before we're ready, and some are waiting, still on their way, moving through dust, around clouds, toward Earth. A star dies, and its light races out into the dark. Centuries later, we see the reflection on the wall of cosmic dust and say, "It happened, and it matters." Some stars do not go gently. Their ends are not measured in soft glows or fading embers. They end in violence so immense it defies analogy, in blasts that ripple through the fabric of the cosmos with energy unmatched by anything else we've observed. These are not supernovae as we typically know them, though they may begin that way. These are gamma-ray bursts, explosions so bright, so focused, so brief and devastating that for a few seconds they can outshine everything else in the observable universe. They arrive without warning. From a galaxy far away, across billions of light years, a narrow beam of radiation erupts, piercing the void like a blade of fire. If that beam happens to be aimed toward Earth, our detectors catch it as a flicker of incomprehensible energy. Most last only a few seconds. Others linger for a few minutes. All of them are over quickly. But in those fleeting moments, the energy released can be more than the sun will emit in its entire 10 billion year life. These bursts come in two main types. Long gamma-ray bursts, lasting more than 2 seconds, are thought to come from the collapse of massive stars, ones so large and unstable that when their cores fall in, they do not stop at neutron stars or even regular black holes. Their death throes launch jets of plasma at nearly the speed of light, focused into beams that drill through the star's outer layers and shoot into space. It's as if the star's death is trying to punch a hole in the universe. Short gamma-ray bursts are different. They're briefer, and they come from collisions. Two neutron stars spiraling into each other, or a neutron star and a black hole caught in a fatal dance. When these objects meet, they do not merge gently. The impact shakes space-time itself, releasing gravitational waves, X-rays, ultraviolet flares, and sometimes a gamma-ray burst. We were blind to them until the mid-20th century. Ironically, it was war that brought them to our attention. In the 1,960 seconds, American satellites meant to detect nuclear tests caught something strange. Bursts of radiation coming from deep space. At first, scientists thought they were malfunctions. Then they realized they were glimpses of events no one had predicted. Brightness from beyond the Milky Way, as if something out there was burning a hole into the record of night. Now we have dozens of satellites watching for them. When one appears, alerts go out across the world in seconds. Telescopes pivot, observatories prepare. For that one moment, all eyes turn toward the dying light of a single catastrophic end. But it's not just the spectacle that draws our attention. There's fear, too. If a gamma-ray burst happened close enough to Earth and its beam was aimed our way, it could destroy life. The radiation would strip away our atmosphere's protective ozone, exposing the surface to ultraviolet light. It could cause mass extinctions, alter the chemistry of our skies, and darken the planet with dust and soot. Some scientists believe such an event might have happened before, long ago, before humans were here to record it. A silent catastrophe from above. Yet the danger is distant. These events are rare. The odds of one occurring close enough to Earth and aimed precisely in our direction are almost vanishingly small. We live in the quiet lanes of the galaxy, far from the star-forming regions where such giants tend to live and die, and the sky, for now, is still dark and calm. But the power of these events remains staggering. We don't just observe them, we learn from them, because they carry information that nothing else can. The gamma-ray burst itself is just the opening note. After the initial flash, we observe the afterglow, a fading ember across the electromagnetic spectrum, from X-rays to radio waves. By watching how that afterglow dims, we can measure the dust around the explosion, the gas of the host galaxy, even the structure of space-time between there and here. Some of the most distant objects we've ever observed have been gamma-ray bursts. They are lighthouses from the early universe, explosions from stars that lived and died when galaxies were still young, when the first heavy elements were just beginning to seed the cosmos. We've seen bursts from billions of light years away. That means the light we see now left before Earth even existed. They are, in a way, messengers from the beginning. Sometimes they arrive alone. Other times they are accompanied by kilonovae, the aftershocks of neutron star collisions that also produce gold, platinum, and other heavy elements. When we wear jewelry, or hold a phone, or carry coins, we carry with us atoms born in these distant, violent deaths, not just forged in stars, but scattered in explosions that shook the sky. And so, not all stars die quietly. Some go out screaming, tearing space with radiation and jets, sending shock waves through galaxies, echoing through time and light and matter. Some leave scars that shine for a moment, brighter than all the galaxies combined. Some leave metals and light and silence in their wake. Even in the grand story of stellar death, there are chapters written in fire, in radiation, in fleeting bursts so bright they seem like errors in the sky. But they are real, they are rare, and they remind us that the universe is not just a place of slow drift and patient cycles. Sometimes it flares. There is a hush spreading across the universe, not a silence of absence, but a dimming, a slowing, a soft exhale after the feverish pulse of youth. In the early cosmos, stars were born in brilliant waves, whole galaxies alight with the fire of creation. Clouds collapsed eagerly, matter clumped and ignited, and starlight spilled across space in dazzling, chaotic bursts. But now, that frenzy is easing. The engines of creation are winding down. The golden age of stars is behind us. It's not that star birth has ceased. It hasn't. But the rhythm has changed. Galaxies that once churned out thousands of suns per year now birth just a few. The great gas reservoirs are thinning. The dense, cold clouds that once fueled stellar nurseries are rarer now, stretched thin by time, scattered by ancient explosions, and siphoned into black holes at galactic centers. The raw ingredients for stars still exist, but they are fewer, more elusive, harder to gather. Still, they come. New stars flicker into life in distant nebulae, glowing pink and blue in photographs, nestled in clouds where starlight has not yet broken through. Their numbers may be fewer, their bursts less furious, but their presence reminds us that the universe, though aging, is not yet still. Starbirth continues, stubborn and quiet, and in the span of time ahead, there will be no sudden stop. The universe doesn't close like a book. It just cools, expands, waits. The stars already formed will live out their lives, each one according to its mass, each one charting a different course toward an inevitable end. The giants will die young and violently. The dwarfs will burn low and long, barely shifting in brightness for trillions of years. Even now, some of the longest living red dwarfs haven't yet reached middle age, though the universe itself is nearly 14 billion years old. When the last new star is born, no one will be there to notice. It will not be grand. Just a quiet flicker in a forgotten part of space, a final act in a play whose audience has long since vanished. After that, the stars will fade one by one, like candles burning through their wax. One goes out, then another, then thousands, and eventually the sky will darken. White dwarfs, those dense, hot cores left behind by smaller stars, will linger for eons. They will cool so slowly that trillions of years may pass before they lose their light. But cool they will, until they become black dwarfs, invisible husks, cold and silent, carrying the shape of the star they once were, but none of its warmth. These too will drift through the dark, pulled only by gravity, untouched, unlit, unseen. And what of the black holes? They too are not eternal. According to our best understanding, even black holes evaporate, not quickly, far from it. A black hole with the mass of our sun would take around 10 to the power of 67 years to vanish completely through Hawking radiation, a timescale so vast it defies all intuition. But in the end, they, too, must go. They will shrink, emit faint radiation, and disappear, leaving nothing behind but a whisper of energy in an empty sky. That future, cold, dark, and patient, is not a tragedy. It is not the death of wonder. It is simply another chapter, one written in the language of entropy and time. It is the natural arc of all things that burn, to eventually flicker out. And yet, the story of stars is still being written. Right now, somewhere in a corner of the cosmos, a new star is catching fire. Its light may not reach us for 1,000 years, but it's already there, blooming into brightness, pulling planets and dust into its orbit, waking up to the laws of gravity and light. Around it, gas is churning, debris is dancing. The ancient recipe continues: collapse, ignition, radiation, death, renewal. And that star will shine for millions or billions of years, indifferent to how late it came to the party. There is still time. Time for discovery, for stargazing, for watching sunsets filtered through Earth's atmosphere, for wondering what it might feel like to stand near another sun. Time for telescopes to catch the birth cries of galaxies far away. Time to imagine what civilizations might rise under the light of stars we will never see. So much of the universe's life is still ahead. Even as the pace slows, Even as the light stretches and the galaxies drift farther apart, the flame hasn't gone out. The stars we know are only a sliver of what will exist. The last red dwarfs will shine for so long that it is almost meaningless to speak of an end. Long after Earth has fallen silent, after our sun has dimmed and vanished, after memory itself has unraveled, the smallest stars will still be glowing. They will light the final ages of the cosmos. And when even they go dark, when the last photon blinks out and the universe becomes a shadow of its former brightness, it won't be an erasure. It will be a memory, a long, luminous memory of stars,